I get the honor of being the first presenter here this morning, so Ray did an excellent job with an overview. My name is Lisa Loden. I'm from the Oak Ridge National Laboratory, and I'm going to be talking here for the next little bit on the front end of the nuclear fuel cycle, what it takes to get the uranium out of the ground and actually process it to a form that it can actually be used for the making fuel for the nuclear reactors. So, very first thing, you really can't talk about the nuclear fuel cycle without talking a little bit about uranium. Uranium is the key element for the nuclear industry. Without it, we wouldn't have the power reactors, the nuclear power reactors that we have. Of course, uranium was discovered in the late 1700s, but it really wasn't appreciated as far as what that element was for nearly 100 years later. It took over 100 years before it was really evaluated. In fact, in the late 1900s, they actually, when Madame Curie was doing her experimentations with radium, it was discovered that uranium was radioactive. And then in the early 20th century, with the advent of discovery of isotopes, that elements had isotopes, that was then continued with research. And up until 1930s, when they really started looking at uranium, they discovered that naturally occurring uranium actually had two isotopes. It had the uranium-238 predominantly, and just a little bit, about 0.7% of the naturally occurring uranium was uranium-235. So with that, we started the discovery, really, that's when the birth of the nuclear industry started. It was in the 30s and early 40s, of course, with the Manhattan Project, with the discovery of fission, the concept of the atomic bomb, and of course the Manhattan Project, which all of us are aware of because that is our legacy in the Department of Energy, is when it's taking those concepts and actually building plants where we could process and recover and enrich and produce enriched uranium that could be used for weapons work and also for reactors, for nuclear power reactors later. In 1942, large complexes were built primarily in Oak Ridge and also at Hanford. In Oak Ridge, that we had huge facilities built for processing and enriching uranium for the use in the war effort. Need for separation. Uranium, as it's mined in from the ground, you can't directly take that and make a fuel out of it and put it in a reactor. There's too many impurities, there's daughter products that occur from the natural decay of uranium that have to be removed. So it's not like coal or gas that you can take and put in a fossil fuel reactor. You have to process it. And so in the front end of the nuclear fuel cycle, that's dedicated to taking the uranium out of the ground, processing it, chemically cleaning it up, and converting it into something that can be used for the nuclear fuel cycle. Again, like I said earlier, uranium, as it occurs naturally, about 0.7% is uranium-235, which is what we really want. That's our fissionable material. The uranium-238 is a predominant isotope that is found in nature. In most reactors, as Ray said, there are some reactors like the Canadian reactors, the CANDUs, that can use natural uranium for a fuel, but by and large, most power reactors in the world, or most nuclear reactors in the world, require enriched uranium. If it's a power reactor, it needs between 3 and 5% U-235. So we have to take that material that occurs naturally, and we have to increase or concentrate the uranium-235 amount from that 0.7% up to the certain percent that we need for the reactors. Whether it's 3 or 5% for power reactors, it could be all the way up 20% or more for research reactors, depending on what their applications are. And there's lots of chemical and physical separation processes that are used to prepare the uranium for use in the reactors to make the fuel for the fabrication. So, and we're talking about mining, milling, conversion, and enrichment. Those are the key, typically known as the front end of the nuclear fuel cycle. And this chart, basically what I'm going to show is just a little simple flow sheet of how the uranium is processed in the front end. First, you start out with the mining and milling. Mining is just nothing more than removing the deposit from the earth. Milling is that first chemical process that you use, the physical processes that are used to separate the uranium from the ore that's extracted from the ground. Then the uranium is taken to a chemical plant where it is purified, converted to your final forms, whether it's dioxides or oxides or metals for fuel, for reactors, or it may be uranium hexafluoride that we convert it to send to an enrichment plant so we can increase the uranium-235 content in it. So the conversion plant is your key chemical plant in the front end fuel processing. Then enrichment is that process that is dedicated to that increasing or concentrating of the U-235 isotope in the uranium. There's two products that come out of the enrichment plant. You get your enriched uranium, which is then sent back to another chemical plant where it is converted back to either a dioxide or a metal for insertion into the fuel fabrication where we make our fuel, the pellets or the elements for loading into the reactor, which is then sent to the nuclear reactor. Or we have another large stream that comes out of the enrichment plant, which is called depleted uranium, and that's the stream that has the less U-235. You put up so much, you put your natural uranium in, you have one stream that comes out of enrichment that is increased in 235 content. You have another stream, which is the bulk of the stream, that has the U-238 and it has a little bit of 235 in it, but it's less than 0.7%. Typically, they run between 0.2 and 0.3% 235 in your tail stream. Now, this chart also gives a little appreciation for the quantities of material that's being processed. If you want to make, say, the 24 tons of uranium as uranium dioxide that's needed to load into a reactor on an annual basis, you have to start out with something on the order of 200 tons of uranium material at the mills and conversion facilities. So these plants on the front end of the fuel cycle are very large and handle quite a large throughput of material for processing. Production-wise and resource-wise, uranium can be found throughout the world, and it is found throughout the world. But there are some key places such as Australia, Kazakhstan, Canada, and Russia. Those are where part of the uranium is mostly found for the resources. And then the United States, of course, is down. We only have, on estimate, now these are fairly low-cost economic recovery materials in the United States, around 200,000 tons of uranium. But the bulk of the uranium is found in Australia and Kazakhstan and Canada. Production-wise, this chart shows basically the various production sites. Again, where the most of the uranium is occurring is where it mostly is being mined at the currently now. Kazakhstan has really taken off in the last 10 years, and they have become the leader in the production of uranium for the world. They've actually last year exceeded Canada and took over the #1 spot. It's estimated that there's, of the 441 reactors operating in the world today, that we need about 69,000 tons of uranium on an annual basis. Currently, the supply that for just the low-cost resources of uranium that we know of that are out in the world, we have at least an 80-year supply and even more than that if they want to get into ones that's more not as economical to recover. So there is uranium there to meet the demand today. This chart I added to show just basically over the last few years who are the leaders in the production of uranium. Again, Kazakhstan is #1 now, with Canada second, Australia third, and then there's a few countries in in Africa that are producing uranium. So those are the key suppliers for the world today. Abundance. you can go and find uranium pretty much anywhere if you look for it. If you dig in the earth, just about anywhere in the earth's crust, you'll find a little uranium. There won't be much. It may be 2 to 4 parts per million. That's about average. In general, a lot of these deposits where we're talking about, like in Canada or other places where they found the uranium, it's about 1% uranium in the ore, or maybe even less than that. There are some deposits, I know there are deposits in Canada right now that have about 20% uranium, but that's rare. It's usually, when we find a deposit of uranium, there's not a lot of it in a deposit. It's maybe 1% or less, so that's why they have to dig up so much rock just to recover that small amount and then extract it and process it. But it is, even though it's, 2 to 4 parts per million, it's still fairly abundant material when you think about it. It's 4 times more abundant than silver and some of the other materials. And there's even been evaluations for recovering it from seawater, because it does exist there too. So it is there. It's just cost a lot. You want to get the richest veins, the richest deposits first, and then go for the others if you can, if that doesn't meet your supply or your demand. Uranium occurs in hundreds of minerals. There are so many, there's tables upon tables upon tables of uranium compounds that you can find in the earth. Predominantly, some of the more common ones are pitchblende, uraninite, autunite. Those are the more common minerals, but it can be found with phosphates, it can be found with monazite sands, which of course where they're doing rare earth processing you can find that, but many, many different compounds of uranium, which makes the chemistry in the mills and the processing up front fairly complex, because we're dealing with so many different types of chemicals that we have to process through. Commercial deposits. Typically you'll find a lot of the commercial deposits that are being mined today are in granites or in sandstones, those types. They're also co-producing uranium. A lot of what comes out of Australia comes from mines where they're actually producing copper or gold. And so when they extract the copper and gold, because uranium is in that ore also, they co-extract it and produce it at the mines too. So making double value on the ore that they're processing. Now, first off, to get the uranium out of the ground, it's pretty much like any other material that you're going to mine. There's traditional ways to mine it. There's non-traditional ways. In the traditional ways, you have surface mining, or what they call open cut mining, and there's the underground mining. In the non-traditional ways, Ray talked a little bit about the in situ, which has really taken off in the last few years, predominantly because of Kazakhstan. Most of their deposits are amenable to in situ mining, and I'll talk a little bit about what that is in a minute. And then, of course, byproducts from other processes where they're producing maybe copper or gold, phosphates. You can recover uranium from those. Still today, as of last year, over 57% of what was produced in the world was still by the traditional means, but the in situ leaching was up to 36%. That will increase over time as we begin to process more and more fields that are amenable to in situ leaching or in situ processing. And you'll see why when I talk about it, from the infrastructure and the cost that's involved in that. It's much cheaper than doing a traditional mining technique. Methods of mining. Of course, underground mining is nothing more than where you dig. You have a deposit deep within the earth, and you have to dig tunnels, access tunnels down to it, or vertical shafts, and then from there remove the uranium by the typical drilling, and you blast it, drill it, remove it out, and bring the rock back up to the surface. Open cut mining is surface mining. That's where you'll take the overburden. Uranium is laying a little closer to the surface of the earth. They'll take and remove the overburden on top of that. You'll see these large pits. I'm from the coal industry, so we're very common. That was very common where I was for strip mining. For coal, well, you can strip mine for uranium. So what you'll typically see at a surface mine, these large pits that are terraced and go down where they're actually accessing to the uranium itself. In situ mining, you don't really remove any rock from the earth. What you do is you pump solution into the ground, dissolve the uranium, and then pump the dissolved uranium to the surface and treat the water or treat the aqueous solution. And so the rock basically stays in place. That's why that's so advantageous. If you can do that, you don't need these big, heavy earth movers and all the infrastructure and everything that goes along with traditional mining. Unfortunately, the deposits, not all deposits are amenable for in situ mining. The choice, again, it all comes down to economics. What's the strength of the grade? How deep is the deposit? What is the overburden that's on top of the deposit? There are many, many factors that go into deciding what is the best way to recover the uranium from the mines. We show a few pictures here, some in Australia. They have all types of mining there. The first one, Olympic Dam. Olympic Dam is a underground mining facility where they are co-processing copper, gold, and uranium at their mill to recover from the ore that's taken out of the ground. The open cut mine at Ranger is a surface mine where they're actually extracting, take the overburden out, and remove the uranium from that. Once they remove the overburden, then they'll dig the uranium up and process that. Now typically when you have a mine, your mill is fairly close to your mine because you're dealing with so much material. Just the transport and location, you will bring their rock up and just convey it over to your mill and do your first initial separation of uranium from the ore at the mill. But in some cases the mill's co-located. If you have several mines in a region, it may be co-located between that so that you can service several mines instead of one mine. In situ leaching on the right of the screen, you basically just have a well field. They drill many, many wells down into the ground, down to the deposit where they can pump the solution down. Then you'll have other wells sitting there where they'll pump the solution back up, send it to, you may have an ion exchange column sitting at the top of the well heads or in the field where you can extract the uranium. Solution is pumped right back down into the ground, and then the resin off the ion exchanges is sent to a mill where it's processed. So,
is that a water solution?
No, you have, depending upon what the deposit is, it may be a slight alkaline solution or very slight acidic, but it's very weak. Yeah. In underground mining, of course, what's used in underground mining for uranium is not any different than what you would use if you were mining for gold or copper or coal or whatever. You're going to have the deep shafts or the access tunnels to get down to the deposit, and then you're going to be blasting and digging to remove the rock from the deposit to bring it to the surface. There's very little overburden disturbed when you're doing underground mining because all the work is below ground. Some of the processing, a lot of times what they'll do is they'll grind and crush and actually do some pre-treatment of the rock underground and sorting before they bring it up to the surface to be processed at the mill. So in some of these mines, I was in Canada last year, and we went down to like 600 meters, and they actually were crushing and grinding the ore as they brought it out of the earth underground, mixing it and making a slurry and pumping that slurry to the surface to the mill and then to containers that were shipped to the mill. So every mine is a little different depending on how they want to set it up and the economics of it, whether they want to bring the rock up and do all the processing at the surface, or if you want to do some processing in the actual mine itself. They can get quite deep, down to 1 kilometer or more depth. And of course, when you get down into the underground mines, you have a lot of costs associated with ventilation, water. There's lots of issues with water and flooding in these mines, so there's a lot of money spent on trying to protect the workers and keep the mines from flooding so that when you access the materials, you can actually do that safely. There are different methods for underground mining. The traditional mining or conventional mining, where they room and pillar, cut and fill. Those are some of the more common methods where they go and remove the ore from the underground. Some of the more emerging processes are called boring processes. They're raise bore, box hole boring, jet boring. This is basically where they will drill a pilot hole down through the deposit, and then they put like a reamer or a borer in, and they just bore out, make that hole bigger. And as they make that hole bigger, the rock will fall down to a collection point at the bottom. They scoop it up, and then that's taken off and processed and brought to the surface. They can be quite elaborate depending upon the deposit and how it lays, but you'll have tunnels. Basically, you'll build your access tunnels coming in and then build over to the deposit, and these tunnels can run off like in many different directions following the veins of material as it lays underground. And there's a lot of exploratory work that is done before you ever get in to start to mine these fields, because they have to understand the geological layout of the deposit and how's the best way to set up their mines underground. Surface mining is not as complex as underground mining. Basically, all you're doing is you're finding a deposit that lies fairly close to the top of the earth, and then you bring it, cut away the overburden to get to the deposit. Again, you've got to have a lot of area. You can see how large these facilities are, or these mines are, so a lot of acreage associated with the surface mine. Terraced mining, the pits will be terraced, and to get down to the deposits themselves. And there's a lot of other minerals. When you come to a surface mine, there's many other minerals that can be mined from open pits, not just uranium when they're mining. In situ leaching, again, this is becoming one of the more common types of mining that's used in the world today as they find new deposits. And basically what you find is a deposit of uranium that's laying between two impermeable layers, like two layers of clay, and it's below the water table. So when you have a deposit like that, then they can pump down, basically drill holes down into the deposit and pump solutions down that will then be pumped across the deposit. And as it passes, the solutions pass across, they dissolve the uranium that's contained in the deposit, and leaving most of it. That solution is preferable for uranium and not for other minerals. So hopefully when you're done, you'll have primarily a uranium solution and not a lot of other contaminants in it. That solution is pumped across and then pumped back up to the top to, like I said earlier, generally anion exchange columns, where the uranium is stripped from the solution onto the resin in the columns, and then the solution is just pumped right back into the ground. You just keep doing that over and over. And then the resin is sent for further processing to remove the uranium from it, and then processed in the conversion facilities. Now, this is great if you have a deposit that is set up like this between two impermeable layers, and primarily this, in the United States, pretty much all uranium that's being mined today is done by in situ leaching in the small mines. They don't do the old traditional mining that we used to, and it's probably economics. It's cheaper to do it this way than to do it the old traditional ways. Another pictures of what it might look like. Here you have many wells in the field. You can see just lines upon lines upon lines of well heads, depending upon the deposit, with maybe one or two buildings sitting there where the resin, the ion exchange facility is. So much less infrastructure for an in situ leaching than for the traditional open cut or underground mining.
Do they just move the connection to different wellheads?
Yes, as they move, what you'll see is they'll have the fields laid out in sections, and they'll work a deposit, and then they'll just move along, and they can move the pipelines as they go and just close off the old wells and just drill in another section and move your piping. Yes?
It would be best for the tape if you repeat the question.
Oh, okay. I'm sorry. Okay. Yes, typically when the deposit is finished, or the uranium is extracted, they just leave the well, drill new wells, move the pipes, and just continue that way for this. So very little infrastructure. Another key material, now this is one that a lot of countries are looking at, especially countries that don't have uranium deposits in general, but they have phosphates, especially in the Middle East. The Middle East is a lot of phosphates in that, and the phosphates contain between 50 and 200 parts per million uranium. And phosphates are used to produce fertilizers, and they process on the order of hundreds of thousands of tons of phosphates a year. So if you have a phosphate plant where you're making phosphoric acid, you can set up a solvent extraction process at the tail end of that, or at the tail end of the phosphoric acid plant, and actually recover the uranium. And there's several countries that are looking at that now. That was big in the 70s and early 80s. Then when the price of uranium dropped, people stopped doing that. There was enough uranium that the fertilizer companies said, we're not going to do this. But I know that they're reevaluating it again. As the demand of uranium increases, more and more countries are starting to look at their phosphate supplies to see if that is an option for them, for their uranium also, to recover their uranium also. So,
Can I ask a question about the volume of water that it takes to do this sort of operation on a typical farm?
on a typical,
Just a process, like how many gallons of water would you say go into this extraction process?
it depends upon what you're doing, what your chemistry is. If you're doing resins and the leachates and all, you're recycling a lot. So that's one of the downfalls for water, needing water and the supplies for a mine or for a mill. That's one of the downfalls, or one of the things that has to be considered when they're processing or locating a mill. Where's the water going to come from? You do need it. Is it millions of gallons? No. Hundreds of thousands of gallons? Maybe. Depends upon the size of the facility. And depends upon the chemistry that's involved as far as how much water you need. And the power. Of course, you need water and electricity.
Right. So you said a lot of it's recycled.
A lot is recycled.
Percentage, just
Probably in that, I would estimate 60-70% or more is recycled. Now, what you'll find when you go to a mill, you will see these large ponds, that they're settling ponds, because at a mill, when you process, you're going to have waste ponds, and they'll let that evaporate. In those cases, you may see a lot of your water goes out into that and gets evaporated up. In other cases, they may let it run down and then recycle back where they can use it. If you have an abundance of water, they don't worry about it. If you don't have a lot of water at your mill, then they're going to recycle everything that they can to keep the costs down. And at the mill, basically what they're going to do is they're going to take that rock that comes from the earth and they're going to process it in order to extract the uranium from the rock or from the ore. So you're going to have the rock delivered or the ore delivered to the plant. There's going to be some initial physical processing of the rock. You want to crush it, grind it. You want to make it high surface area so that you can start doing some chemical processing of it. So they will grind it down to a fine powder typically. And then they'll use either an acid or an alkali, depending upon the mineral of the rock, to dissolve the uranium or leach the uranium out of the rock. Once that uranium is in solution, there's a lot of solids that are not dissolved, so you have to separate those solids in the slurry from the actual solution. And they'll use filtration units, large filtration units. They'll also use clarification units where they will flocculate and increase the size of the particles so they'll drop down and separate from the solution itself. And those will go out to what's called a tailings pond or waste piles. And you'll have large portions of that because the bulk of what you send to the mill is waste. You're only trying to get that less than 1% material that's in that's uranium. You want everything else to go out as your waste stream. So you'll have these mountains of waste piles or these big settling ponds associated with the mill itself, where that come from once the uranium is separated. Now, once you've got the uranium solution separated from the other materials, then they can do the precipitation, and typically they'll use ammonia and form an ammonium diuranate. In some cases, they use ammonia and carbon dioxide, and they'll form an ammonium uranyl tricarbonate. And in some cases, there's some mills that actually use peroxide and do some precipitation cleanup or purification with precipitation, so they'll use and form a urinal peroxide. So the chemistries vary depending upon the mills and how they want to set them up. Now, some plants will produce, like I said, the ammonium diurenate or the ammonium urinal carbonates. In some plants or some mills, they actually take it on and oxidize it and convert it on to an oxide form. But anything, I'm sure you all have heard of yellow cake or uranium ore concentrate. The product of the mill is yellow cake. But it may not be yellow at all. It may be black. It may be an oxide. If it's an oxide, it can be as black as coal. It can be brown. It can be red. It can be yellow. That's just yellow cake's just a colloquial term that's used. It's the product of the mill. More recently, we call it now uranium ore concentrate instead of yellow cake. And then it's typically packaged in 55-gallon drums or 200-liter drums and shipped on that way to the conversion facilities for further processing. Uranium conversion processes, the bulk of uranium, the primary process, the primary objective of uranium conversion process is to purify that uranium ore concentrate or yellow cake that's produced at the mill, and to convert it into a form that can then be either sent to a fuel fab to make oxide fuel pellets or to an enrichment facility where you can increase the uranium-235. There's two methods that are used throughout the world for uranium conversion processing. There's the wet process and the dry process. 99% of all uranium that's processed in conversion facilities in the world use the wet process, which I'll talk about in just a minute. The dry process, currently there's only one plant in the world that is actually using that process, and it's the one here at Metropolis, Illinois. And the big difference in them is, where do you remove the impurities? Do you remove the impurities at the front end of the conversion process, or do you wait and do your impurity removal at the back end of the process, which is what happens with fractional distillation at the back end of the dry process? So, again, most people in the world are using the wet process, but we have to mention the dry because there is that one facility in the world that does that unique processing. Now, conversion facilities throughout the world, they're needed. We have to have the material to meet the product specs for the reactors. In order to make that, we have to do purification, and that's done in conversion. There's basically right now, essentially the demand is for about 60,000 tons of purified material for the reactors. There's 5 major companies that are doing the bulk of the conversion work in the world. It's Areva in France, Cameco in Canada, Converdyne, that's the one that does the dry processing in Metropolis, Illinois, Springfields, which is in Great Britain, and then 10X in Russia. Those are your main players in the conversion facilities. So they will buy up the yellow cake that's being produced at the mines, have contracts with the various power industry reactor owners, and produce the purified material for them to feed into their enrichment facilities or to feed directly to their fuel fabrication plants. The wet conversion process typically follows the same chemistry that Ray talked about in Purex. They basically take the uranium ore concentrate, dissolve it in nitric acid, form a urinal nitrate. The urinal nitrate is then purified using solvent extraction, and the preferred solvent extraction is tributyl phosphate diluted down with kerosene. Now, typically you will see in the conversion facilities mixer settlers where you're dealing with large quantities, and that's at the mill because there are extraction units actually at the mills themselves. When you get to the conversion facilities, you're more likely to see pulse columns than mixer settlers because you're decreasing the volume of material as you step from a mill to a conversion facility. And so the preferred methods typically are the pulse columns at these conversion plants. But again, what we're doing is using solvent extraction to recover the uranium, separate it from the aqueous solution that has all the impurities in it. Then we remove the purified uranium from the extractant or the organic. and then precipitate it into a solid form, again usually using ammonia to form an ammonium diurenate. That ammonium diurenate can then be heated in air at high temperatures to convert it over to an oxide form. The oxide can be reacted with hydrogen to form UO2, and that UO2 that could then be sent to fuel fabricators to make fuel if you need it for natural uranium. If you need to make feed for an enrichment facility, which by and large is uranium hexafluoride, then we would take that UO2, mix it with hydrogen fluoride, form uranium tetrafluoride. Then we would combine the uranium tetrafluoride with fluorine to form uranium hexafluoride. And uranium hexafluoride is then shipped in cylinders to the enrichment facilities where it's processed to enrich the uranium. So, got that chemistry? There's a test. It's pretty simple. It just depends on what your final product is. What is your final product of your conversion? Is it going to be UF6? Is it going to be UO2? Is it, if you were using, say, an EMIS facility to enrich uranium, it would be uranium tetrachloride. So it just depends on who your final customer is, what you're making. It's just, think of a conversion facility as a large chemical plant that has many versatile processes in it, depending to make that final purified product that can be used. And this is the step for making enriched, taking it through with the uranium tetrafluoride to uranium hexafluoride. The dry conversion process is a little different from the wet conversion process in that you've got fairly pure uranium ore concentrate coming in. So they will take that and convert it to your oxides and then a UF4 to, well, they take the UO2 and heat it under hydrogen to make UO2. Then the UO2 is processed with hydrogen fluoride to make UF4. The UF4 is processed to make UF6, but now there's impurities in there because we've not done any extraction processing, or we've not done any type of treatment on that material. We're just basically chemically converting it from one form to another. So at the end, the UF6 that's produced has some impurities in it, but we can separate those impurities from the UF6 by doing fractional distillation. And so instead of doing solvent extraction at the front end like it's done in wet processing, in dry processing you have a fractional distillation column at the back end where you clean up that final UF6 that's formed to make your purified product for enrichment. Two pictures. One shows covered ion. This is the dry process in Metropolis, Illinois. And this is British Nuclear Fuels Plant in Springfields, UK, which is a wet process. And again, by and large, 99% of all uranium that's being converted today from the ore, from the mills to a product is done by the wet processing method. Now, uranium enrichment if we need uranium, enriched uranium for the reactors, we basically need to send it to an enrichment facility. Currently, of the reactors that are operating today, the majority of your power reactors do require that 3 to 5% uranium-235. So there's a demand for about what we call SWU. That's our terms that are used in enrichment. That's the measurement of work that's done or energy that's done to produce a kilogram of enriched uranium at a specific enrichment and with a specific tails or waste stream that's there. And we say for the 441 reactors that are in operation today, they need between 45 million and 50 million SWU per year. There is currently facilities capable, already built, that can meet those, somewhere on the order of 58 million SWU per year being produced or could be produced. Now these vary. As old plants go down, the old gaseous diffusion plants are being closed. Gas centrifuge plants are being built. You never know what the Russians, if they're going to glut the market, what they're going to send out on the market as the treaties are signed and they're able to downblend their warheads to natural or to 3 to 5% uranium. So there's many factors that affect the supply of enriched uranium in the world and the capacity for the facilities. Old plants, a lot of the old gaseous diffusion plants are being replaced by the gas centrifuge technology. That is the preferred technology today. And one of the main reasons is it's just more energy efficient. In a gaseous diffusion plant, in order to process just one SWU, it takes about 2,500 kilowatts of power. In a centrifuge, that's one machine. In a centrifuge plant, it takes about 50 kilowatts per hour, or hour, to process. So much less energy requirements, so you don't need the big power plants and the water cooling plants and the things that at a gas centrifuge plant that you would need, like you would see at a gaseous diffusion plant. There's been many methods that have been developed for enriching uranium, and the key is these are for increasing that uranium-235 content from 0.7% all the way up to 90+% uranium, depending on what you want your final uranium product to be. One of the very first, what was developed during the Manhattan days, was called the calutrons, and we'll talk a little bit about what the calutron was. The first large commercial plant for enriching uranium was gaseous diffusion. Gas centrifuge is the most efficient, and it's currently the way that everybody that's in the business today or getting into the business today is using gas centrifuge. There were, like the South Africans, using aerodynamic nozzle, as Ray mentioned earlier, for enriching uranium. Laser excitation, are using lasers to separate the uranium-235 from uranium-238 and to increase the concentration of U-235, has been studied in R&D and in some has been demonstrated, but there's no commercial plants that have ever been built using laser excitation yet. And then chemical exchange and ion exchange have been evaluated as a method to do enrichment of uranium, but no really large-scale commercial facilities are online. They're more have concentrated in the field for enriching using gas centrifuge and gaseous diffusion. That's been the two primary commercial plants to date. Now, calutron is nothing more than it's a mass spectrometer. It's basically based on a mass spectrometry. A lot of work was done in the in the 1930s on the separation or using mass specs and separations and studies of uranium using this concept. A lot of work was done at the University of California by Dr. Lawrence using what they called a cyclotron. So the calutron that came out of that was basically named from University of California for California U and tron for the cyclotron. Now what happens in a calutron is basically you take uranium and you ionize it. And when you ionize it, you pass it through a magnetic field. And when it moves through the magnetic field, the two isotopes will take a slightly different pathway. And so we take advantage of that slightly different turn or a slightly different path that they take, and we put receivers on the other side. So as the ions come up, they pass through the magnetic field and they turn, and they travel at a slightly different path. We have receiver pods at the other end, and we catch them. So the uranium-235, hopefully, if they're separated enough, you can get, and don't get crossovers between the beams or between the paths, you can actually collect uranium-235 in one pot and uranium-238 in the other pot. That's the theory. And it did work. I mean, it worked enough for us to produce our first uranium, enriched uranium for the Manhattan Project using calutrons. In fact, the actual cyclotron, you can give you appreciation, the original cyclotrons were like 37 inches in diameter machines. The first calutrons, we call the alpha calutrons, they first estimated they would be the first prototypes were like 184 inches in diameter machines, producing about 4 grams of enriched uranium a day, using 10 of these machines. Well, the war effort during the Manhattan Project, that wasn't good enough. It wasn't enough. We needed the material then, and so that was not fast enough production. So they actually, when they built the plants in Oak Ridge, the the calutrons that were built were 24 times bigger than the 184-inch machines. They're fairly large facilities. In fact, the buildings where they were built, these are large vacuum tanks that these magnets and the calutrons are in. They were 122 feet long by 77 feet wide and 15 feet high, so fairly large facilities. And we actually, when they were building it, they needed copper to wind around the magnets. There was no copper to be found because it was a war effort and copper was in short supply. So the folks in Oak Ridge had to go to the government and say, we need your silver. And they actually took silver out of the mints and brought them in and made their windings with silver to wrap around the magnets so that we could operate the magnets and produce the uranium. And then when the war was over, we had to send all that silver back. So, and I think it was, the accountability was great on it. There was very little loss. Yeah, it was great, which I'm surprised. That was a lot of silver that was moved. There were also the original, we had alpha and beta calutrons because we needed to produce quickly the enriched uranium. The alpha calutrons would enrich their uranium up to from 0.7% to 12% U-235. The beta calutrons then took it on up to 99+% 235, or basically made the final highly enriched uranium. We still have a beta calutron that's been preserved at Oak Ridge at the Y12 plant. This shows you can see the magnets here. This is the actual unit itself. We did continue even after the actual calutrons were decommissioned in the 1950s for uranium enrichment, but we continued to keep beta calutrons operating to make stable isotopes for the medical and research fields. And they do have tours periodically, and if you're ever in Oak Ridge and they have one at Y12, I'd encourage you to do that because I think it is our legacy. It's one of the things.
Yeah, I got a tour by the guy that's on that DVD.
Yeah. Ray Smith?
Yeah.
Yes. I spent 25 years at Y12, so this is my playground.
Yeah.
Yeah, if you ever get to Oak Ridge and they're giving a tour, I'd encourage you to go through and see it. They've really preserved it. Yeah.
They even had that girl that worked there. She would come back.
We had, in Oak Ridge, we had what you call the Calutron girls, and they operated the electronics in the past. They didn't know what they were doing,
Right.
but they knew that they had to keep the dials set a certain way, and they had to stay under certain parameters, and they were much better than the engineers. In fact, they would shoo the engineers off and say, leave it alone. All you're doing is messing it up because you're tweaking it. We know what we're doing. So, and it was those women that basically made the enriched uranium for the war effort.
But they had a picture one, and,
yeah.
and she actually came back.
And she was there, yes.
Yeah.
I think last year they had a big celebration with them. Mm-hmm. There's not many of the women that work there still left. I mean, our generation, that generation is leaving us, unfortunately. Gaseous diffusion was also being developed and was developed during the Manhattan Project. And it took over for basically the calutrons right as soon as they could. It actually was built to supplement the calutrons and then eventually took over and the calutrons were decommissioned. Gaseous diffusion takes advantage of the difference in the weights between the 235 and 238. Basically what they do is they pressurize that uranium hexafluoride gas and then send it through a porous material called a barrier. And the 235 being slightly less in weight than the 238 moves a little faster. So you can get an increase in the 235 on the low pressure side just because the 235 ions or 235 isotopes are moving, atoms are moving a little bit faster than the 238, so the more of them get through the porous material. And then we collect, this is our product side, this would be our tail side, and they would go to different machines. Now in these plants you still need large quantities of machines. You may have 3,500 machines or 5,000 machines operating in a plant with these materials. So it's not one machine that takes you from 0.7% up to 99% or 5% or whatever. You still have lots of machines processing. You have condensers, you have heat exchangers, you have compressors, so large energy requirements to compress the gas and then cool the gas down to go from one machine to another. So that's where the energy requirements come from. large plant at the time, the K-25 plant, which I think is pretty much, they're dismantling it now. But in 1945, this was the largest building in the world. It was a half a mile long, 1,000 feet wide, and covered about 2 million square feet. It was huge. I got the honor of going through there when I first started in the operations in engineering and would support them. And it took a long time to get around that plant. But one of the largest, and this is where the actual machines were operating that was enriching the uranium. After the war, gaseous diffusion became the method that was used after World War II for enriching uranium. There were plants in the United States in Oak Ridge and Portsmouth and Paducah, Kentucky, and Portsmouth, Ohio. There were plants in Russia, plants in France, and plants in China that have gaseous diffusion technology. But the method today that everybody's going to, since I guess about the 70s, has been gas centrifuge. And basically, again, this is another method that's taking advantage of the difference in the weights between 235 and 238. And you basically send the gaseous uranium hexafluoride through a high-speed spinning rotor. The gas is introduced into a rotor that's spinning really fast. And just like the carnival ride, you know, when you get on a carnival ride and they spin you real fast, what happens? It slings you to the outside. The 238 gets slung the farthest, so it's along the wall of the rotor. And the 235 is a little closer to the center of the axis. So they can take advantage of that and scoop out that concentrated 235. Now, in these plants, you have hundreds of thousands of machines running. It's not just one, depending upon what your enrichment level is. So when you go into a plant, you'll see just rows upon rows upon rows of machines. And each one of those is doing a little bit of enrichment. Maybe gram quantity is a small fraction, and you just go from one machine to another to another. But the advantage is they're modular. So you can take and put in, go from one module to another and just expand it as needed, depending upon what your enrichment requirements are. Currently, there's 4 new plants being built for gas centrifuge, and one is in France. 3 are in the United States. The ones being built in the United States, one is Urenco, I think it's in southern New Mexico. Areva is in, I believe, Idaho. And then we have USEC, which is United States Enrichment Corporation, in Ohio. Those are the total. When those are built, these new plants are built, they should meet like 15 million SWU per year. So a large chunk of what's needed would be produced by these new centrifuge plants. There's also gas centrifuge plants. Brazil has a gas centrifuge plant. Iran has pilot plant. They also are building production scale plants in 2 locations in their country. Laser excitation. This is a little different from gas centrifuge and gaseous diffusion in that in this case they take advantage that you can excite the uranium-235 ion a little different from the U-238 ion with laser light. So by doing this, you can ionize the material, excite it with, fine-tune your laser to focus in on the 234, excite that 235, or excite the 235 ion, and then collect it on a collection plate, and the 238 ion just passes along and is never bothered by the laser light. This has been done, demonstrated in research facilities. There have been demonstration plants built, but in fact there is a plant being built today based on laser excitation in North Carolina. It's the Silex plant. It's GE is doing that currently. So it is being built to show a demonstration plant there in North Carolina. The others, the AVLIS and MLIS, AVLIS was advanced laser isotope separation, MLIS was molecular laser isotope separation. Those have been demonstrated on a research scale, but neither was actually taken to a full commercial scale processing. Although lots of countries still do work in it and they're still evaluating it. They basically focusing, seems like today, more on gas centrifuge than on laser technologies, other than this Silex process.
That's still research?
That is actually taking the silex. They're actually building a demonstration plant, bringing it out of the research and into an upscale plant
That's corn.
in North Carolina at Wilmington. Hmm. It's very proprietary. We do not get the full details of it, but yeah, it's ongoing now. Other methods that have been tried, two others basically that were done was the chemical, as Ray mentioned earlier, using either chemical extraction, solvent extraction, or ion exchange. Very little separation there. It's very small when you compare the separations or enrichment factors for those technologies versus what you could get with gaseous diffusion or gas centrifuge. Very large scale plants. Never was really taken further because it boiled down to economics. You just couldn't enrich uranium for as cheap as you could do what it would cost for doing gas centrifuge or gaseous diffusion. The South Africans actually did use aerodynamics. They produced their nuclear weapons using that technology, but when they signed the NPT, they basically gave up that technology. They're the only ones that actually produced material that we know of using the aerodynamic process.
And that is the mass difference again?
That is speed. It's again acceleration. You take it, you increase it through. You basically send a gaseous material through a nozzle, a high-speed nozzle, and when it makes that turn out of that nozzle, then you get that separation, that speed.
Okay.
235 is moving a little faster than the 238, and so when it separates, you can grab it. So in summary, the front end of the process, the nuclear fuel cycle, is basically milling, mining, conversion, and enrichment. Depending on what you will either use a conversion or use enrichment. If you're going to produce UO2 for a natural reactor, fueled reactor, then you don't need enrichment. If you buy, most materials do need enrichment for reactors, 3 to 5%. So we'll either send it to today it's either going to a gaseous diffusion or a gas centrifuge plant where that uranium-235 is being increased from the 0.7% to the 3 to 5% or higher, depending on what the reactor demands for their fuel. It's chemical. Basically, the front end of the fuel cycle is chemical and physical separation processes. It's very versatile because it has to be versatile to take into all the various types of uranium compounds, minerals that are extracted from the earth and processed. And then, of course, the widely used today for enrichment is, like I said, gas centrifuge, gaseous diffusion. But there's still some work being done with the laser excitation with the silex plant, so that's something to continue to watch. And this little cartoon, we finish up with a little cartoon. You have your one little U-235 atom sitting there among all that 238 in nature. He's all alone, but he says, look, I'm special. I'm here, I'm special. And he says, but you think you got problems. The poor 235 or 238 feels blue. He says, but I'm unfissionable. You're special and I'm unfissionable. And so, oh yeah, you're only 3 neutrons overweight. You're okay. He says, and you think you really got problems. So this guy goes like, says, you think you really got problems and you think you've seen troubles? What do you get to enrichment? You really, you're going to be really start separating us from the 235. So just a cute little cartoon to end it.